Dear colleagues, let's consider an example of matrix games. We consider two companies A and B. The first company advertises product on radio, television and newspapers. The second company B advertises the product on radio, television, newspapers and brochures. Payoff matrix of the first player is represented at the first table. Let's find equilibrium in this game. To find equilibrium, let's consider theorem 5.5. And we consider lower value of the game and upper value of the game, and if they are equal to each other, equilibrium exists. Let's copy this matrix and let's consider this example in Excel. We consider the first list of our file and we copy the payoff matrix here. And let's consider minimum values of the first player's payoff for each of his pure strategies. Let's start with the first strategy, radio. The minimum value we will find in the cell G6. For this reason, we will use the function of Excel which is minimum. And we consider the values of the first row, and minimum is -3. And let's consider the second row, and minimum is 5. And the minimum for the last pure strategy of the first player when he uses newspapers is -9. Let's find maximum of these volumes. And the lower value of the game is 5. Now we would like to find min-max or upper value of the game. And for this reason we start with columns of our matrix. And for each column we should find maximum volume, and after that we should find minimum of these maximums. Let us start with the first pure strategy of the second player, radio, and the maximum value of his loss for this strategy we will find in the cell B10. For this reason let us choose the function max, and we find the maximum value of the first column. It is 8. We do the same for the second column and we find maximum for the second column, and it is 5. Also we may find maximum for the third column, and maximum loss of the second player is 9. And also we consider the last column, and maximum loss of the second player here is 8. Now let's find minimum values from these maximums, and minimum value equals 5. And as we can see, maximin equals minimax, or lower value of the game equals upper value of the game. According to the theorem 5.5, in this game there exists an equilibrium in pure strategies. So let us find this equilibrium. Equilibrium in this case consists of maximin strategy of the first player and min-max strategy of the second player. Let us find the maximin strategy of the first player. We look at the lower value of the game, it is 5, and this value 5 corresponds to the second strategy of the first player, A2, television. We highlight this strategy with blue color. And also, let's look at the upper value of the game, it is 5. And this upper value of the game corresponds to the second strategy of the second player, B2, television. And we highlight this strategy also. As a result, the equilibrium in this game is A2, B2. Highlight equilibrium with blue color. The value of the game is 5. And also highlight this with the red color. The solution is found. Let's go back to the verbal model. Now, we should solve the problem if the matrix has the following form. For this reason, once again, we should check if the lower of the game equals to the upper value of the game. Let's copy this matrix and continue with Excel. We continue with the second list in Excel and we copy a matrix here. And once again, let's consider minimum values for the strategies of the first player. We consider the first strategy We consider the second strategy, and we consider the third strategy. As a result, we found minimum values for each of these rows. Now let's find maximum values of these numbers. And lower value of the game is 3. Now let's continue with the upper value of the game, and once again let's consider maximum values for each of the columns. For the first column, maximum is 8. For the second, the maximum is 4. And 9 for the third one. And 8 for the last one. Let's find minimum of these numbers. And upper value of the game is 4. As we can see, the lower value of the game is less than upper value of the game. So lower value of the game is 3, upper value of the game is 4. According to the theorem 5.5, there is no equilibrium in pure strategies in this game. But there is an equilibrium in mixed strategies in each matrix game. To find an equilibrium in mixed strategies, let's consider a method represented in the paragraph 5.9 and solve a matrix game with a pair of dual LP problems. For this reason, let's consider the next list in our Excel file. Here we copy our pair of matrix for the second case. And now let's go back to the paragraph 5.9. We see that this method could be implemented only when all the elements of the pair of matrix are non-negative. In our matrix we see that there are negative numbers. Let us add a constant to each element of this matrix to obtain the matrix without negative volumes. For this reason, let's find the minimum value of these values. The minimum value is -9. Now let's consider a constant which we may add to all the elements. For this reason, let's consider the absolute value of minimum element of our matrix. And let us add the unit to this absolute value. For us it doesn't matter, we may add 1, 2, 3, any number. We just need to find a new matrix without negative payoffs. And as a result, our constant is 10. Let us add this constant to all the elements of our payoff matrix. Now we see that all the elements of new matrix are non-negative. Let's go back to the paragraph 5.9 and let's consider the first linear programming problem. Here we see objective function, it is the sum of the variables xi. The number of these variables equals the number of the pure strategies of the first player. In our case, there are 3 strategies of the first player, A1, A2 and A3. Therefore, there are 3 variables in the first linear programming problem for minimization. Variables of the first linear programming model we will introduce in the red frame in the column G. Let's consider the objective function for minimization linear programming problem for our case. For this case, we need to consider minimization. And let's insert the objective function into the cell G15. In the mathematical model, we should consider the inequality for each of the pure strategy of the second player. So we consider the first column in our table, and we consider our variables xi1, xi2 and xi3. They are in the column G. So, and the restrictions as a result will be 18 times xi1 plus 16 times xi2 plus 8 times xi3. And this sum should be none less than unit. Let us add this restriction into our mathematical model. Let's consider the second pure strategy of the second player, j equals 2. For this reason, we consider the second column in our matrix, and the left-hand side of the second restriction will be 8 times xc1, 13 times xc2, plus 14 times xc3. And once again, it should be none less than unit. Let us add this restriction into the mathematical model. The next restriction we consider for the third pure strategy of the second player. And therefore we need to consider the third column of our table, and the restriction will be the following: 19 times xc1 plus 16 times xc2 plus 1 times xc3, and it should be none less than unit. Let us add this restriction into the mathematical model. And let's consider the last pure strategy of the second player and the last column in the table. So the fourth restriction in our mathematical model will be 7 times xc1 plus 18 times xc2 plus 15 times xc3, and it should be none less than unit. Let us add this restriction into the mathematical model. And all our variables xc1, xc2 and xc3 should be non-negative. And let's add this restriction also. Now let's add these restrictions into Excel file. So the left hand side of the first restriction, 18 times xc1 plus 16 times xc2 plus 8 times xc3, we insert into the cell B18. So for this reason, let's consider sum product function. And the first array, it is the values of the first column. And the second array, it is our variables xc1, xc2 and xc3. They are in the column G, the red frame. So the first restriction is ready. So the left hand side of the first restriction is ready. So let's continue with the left hand side of the second restriction. The left hand side of the second restriction we introduce in the cell C18. And we once again call the function sum product, and the first array, it is the elements 8, 13 and 14 elements of the second column, and array number 2, it is the array of our variables xc1, xc2 and xc3. Okay, and the left hand side of the third restriction we add into the cell D18, and once again we call the function sum product, and the first array, it is the elements of the third column of our matrix, and array number 2, it is our variables xc1, xc2 and xc3. And let us add the left hand side of the fourth restriction, and we insert this left hand side into the cell E18, and once again we call the sum product function, and we choose the elements of the fourth column, and the second array, it is the variables xc1, xc2 and xc3, and as a result the left hand sides are represented in our Excel file. Now let us add the right hand side's units, and these units we insert into the row number 12 for the first restriction, for the second, third and for the last one. Now we are about to find an optimal solution to the first linear programming problem for minimization. Before we do this, I remind you that when we find an optimal solution xc1, xc2, xc3, it will not be the optimal strategy of the first player. After that we should do some calculations, and after these calculations we will find an optimal strategy of the first player. So let's find an optimal solution to the first linear programming problem. For this reason we need optimizer solver, and to install solver we should go to File, Options, Addings, Go, and choose the option Solver Adding. And after that we go to the data and choose solver, and the first field here is the objective function. Objective function, the sum of the variables xc1, xc2 and xc3 is in the cell G15. According to our problem statement, we need to minimize this objective function. The next step, we should choose our variables. They are in the column number G, red frame. Let us add the restrictions. We add the left-hand sides of our restrictions, which are in the row number 18, and they should be none less than unit, and units are represented in the 12th row. Also, our variables should be non-negative, and let's make unconstrained variables non-negative. Let's choose the corresponding option. Everything is ready, and let us find an optimal solution. Solution is found and solution is represented in the red frame in the column G. Now let us calculate the optimal strategy of the first player. For this reason, first of all, let us calculate parameter theta. Theta, it is just the value of the linear programming problem. To calculate theta, we just need to find the sum of the elements of the optimal solution of the first linear programming problem. And theta is represented in the cell G15. Also, we need to find the elements of the optimal solution of the linear programming problem. Xc1 with line, so is represented in the cell G12. Xc2 with line is represented in the cell G13. And Xc3 with line is represented in the cell G14. And now we should calculate the elements of the optimal strategy of the first player as follows, according to this fraction. And the first element of the optimal strategy, Xc1 star, we will find in the cell G24. So we consider the fraction Xc with line 1 over theta, and it is 0. And let's calculate the second element of the optimal strategy of the first player. So it is Xc with line 2 over theta, and it is 0.8125. And let us find the last element of the optimal strategy of the first player. It is Xc3 with line over theta, and it is 0.1875. And let us consider the value of the game. It could be found as 1 over theta, but we should take in mind that we added before a constant 10, and now we should subtract this constant from our fraction 1 over theta. We will find the value of the game in the cell G28. So it is 1 over theta minus our constant, which equals 10. And the value of the game is 3.1875. Now let's consider the second linear programming problem. So the objective function here, it is the sum of 4 variables, and we need to maximize this sum. Let's consider the restrictions. For this linear programming problem, we should consider this restriction for all the pure strategies of the first player. In our case, there are 3 pure strategies of the first player, and therefore here we consider 3 restrictions. And the first restriction corresponds to the first pure strategy of the first player. Variables eta1, eta2, eta3 and eta4 we will insert into the 16th row in the red frame. And objective function, it is the sum of these variables, we will introduce in the cell F16. Let's consider the restrictions. We should consider a restriction for each pure strategy of the first player, and there are 3 pure strategies of the first player, and therefore it will be 3 restrictions for our linear programming problem. And if we consider the first pure strategy of the first player, so it is the first row of our table, and as a result the left hand side of the first restriction will be 18 times eta1 plus 8 times eta2 plus 19 times eta3 and plus 7 times eta4, and this should be less so equal unit. Let us add the first restriction into the mathematical model. And let us add the left hand side of the first restriction into the cell H12. For this reason we call the function sum product, and we choose the first row of this table, and the second array is the array of our variables. So the left hand side of the restriction is represented, and the right hand side unit we insert into the cell G12. Let's consider the second restriction. It corresponds to the second pure strategy of the first player, and for this reason we should consider the second row of our table. And therefore the left hand side of the second restriction will be 16 times eta1 plus 13 times eta2 plus 16 times eta3 plus 18 times eta4, and it should be less or equal unit. Let us add this restriction into the mathematical model. And also let us add the left hand side of this restriction into the cell H13. For this reason we call the function SumProduct, and we choose the second row of our table as array 1, and we choose the second array our variables eta1, eta2, 3 and 4. And let us add the right hand side unit into the cell G13. And now let's consider the third restriction. It corresponds to the third pure strategy of the first player, so we need to consider the third row in our table, and therefore our left hand side of the third restriction will be 8 times eta1 plus 14 times eta2 plus 1 times eta3 plus 15 times eta4, and it should be less or equal unit. Let us add this restriction into the mathematical model. And let us add the left hand side of this restriction into the cell H14. For this reason we call the function SumProduct, and the first array it is the elements of the third row of our table, and the second array it is the array of our variables eta1, 2, 3 and 4. And also we should add the right hand side unit into the cell G14. Also our variables are non-negative. Let us add this restriction into the mathematical model. Let us find an optimal solution to the second linear programming problem, and after that we will calculate the optimal strategy of the second player. We will find an optimal solution to the second problem with Solver. Before we continue with optimal solution in Solver, we should clean this from the previous calculations. We go to the data, we open Solver, we delete all of the previous data, and let us fill with the new data. The objective function now is in the cell F16, and according to the problem statement we need to maximize our objective function. We choose the corresponding option, maximization. Next we choose the variables. They are in the red frame in the 16th row. And let us add the restrictions. The left hand side of our restrictions are in the cells H12, H13 and H14, and the sign is less or equal according to our statement, and the right hand side units are in the column J. And also we should add the restrictions that all the variables are non-negative, and we keep this selection here, make unconstrained variables non-negative. Let us find an optimal solution. Optimal solution to linear programming problem is found, and now we may find an optimal strategy of the second player. To find an optimal strategy of the second player, we should consider the following fraction. And for instance, to calculate the first element of the optimal strategy of the second player, eta1 star, we should calculate the fraction eta1 with line over theta. In our Excel file, eta1 with line is in the cell B16 and theta is in the cell F16. So let us calculate eta1 with star equals B16 over F16. The same way, let us calculate the second element of the optimal strategy of the second player. It is eta1 with line in the cell C16 over theta in the cell F16. Now let us calculate the third element of the optimal strategy of the second player, and it is eta3 with line, it is the cell D16 over theta. And let's calculate the fourth element of the optimal strategy of the second player. It is eta4 with line in the cell E16 over theta. That's it. As a result, we found an optimal strategy of the first player X star, which consists of these three elements. And we found optimal strategy of the second player Y star, which consists of these four elements. And we found an equilibrium X star, Y star, and it is the equilibrium in mixed strategies. Many thanks for attention. See you.